Okay, good afternoon, everyone. So we will start from the last point that we have stopped last week. We talked about the trace element behavior in magnetic systems. Okay. So you can see we defined some categories of elements and mentioned about compatibility and incompatibility as well, right? Their preference, based on their preference to incorporate into the melt or the solid. So those elements which like most to be incorporated into the solid phase is called compatible elements, and those elements which prefer melt phase we call incompatible elements. Okay. So during partial melting, we get the mantle melted, and we remain with the residue, right? In addition to the melt, we are remain with the residue. That's why we term it as partial melting. So since there are two phases resulting, the elements which were available in the original melt will be preferentially fractionated into one of these phases. Okay, so this is what happens in partial melting, and also even in fractional crystallization also the same thing will happen, right? So this fractionation is important for fractionation of elements, right? So this is important due to during igneous melting, whatever the melting mechanism. Okay, we are going to discuss different mechanisms in the future classes, so that we see these elements, different groups of elements, how can they behave under different melting processes. Okay, right. So you can see their behavior in comparison to the major elements, right? So this image is coming from a book called this one, Introduction to Igneous and Metamorphic Petrology. Okay, so probably this book might be available at the science library. Please check that one because it simply describes about these principles. Okay, so you can see the variation of major elements in this case, right? So we have to talk about the trace elements, but first we'll see the variation of major elements and compare them with the trace elements, right? So aluminum, iron, sodium, potassium like elements, right? They are major elements, but you can see their contents. Originally, suppose here, for example, sodium, it's like 3% or so, okay, 2.5 or something like that. And all the after crystallization or after melting or whatever the process has finished, that means a huge range of silica composition you can see here, right? From 45 to 75, right? That means starting from mafic, this end is mafic, actually ultramafic, not mafic, ultramafic, and very felsic granitic compositions, very felsic compositions, right? So that means almost all the melting systems are incorporated in this silica variation range. Okay, so that means all the melts produced in the mantle or within the earth are covered under this major element variation, silica major element variation. But still you can see the lowest end is like 2.5 weight percent sodium in this case. Okay, forget about silica variation now. Now let's see how other elements with respect to silica has changed. Okay, so you can see here it's like 5%. It's like 5%. So only 2.5 to 5%, like very small range. Okay, and even potassium from 0 to like 3%. And iron, if you take, it's like 3 to 10. Aluminium maybe 15 to uh, 18, 17, like that, right? So likewise, even silica, it's not very big change, right? It's just 40 to 75, even less than twice, right? It's not a twofold increase. So what is the magnitude we are talking about here? The magnitude of major element changes, right? It's very small, right? It's not like 3 times, not like 4 times, 5 times, like such big change is not there visible in this is igneous system. All the igneous rocks are included here, right? But if you compare that with trace elements, for example, nickel, we have one trace element here, nickel, and another one is here, zirconium, right? But for the same range of silica composition, right? That means it should cover all the rock types, okay? From ultramafic to felsic, highly felsic. What about the variation? Maybe like 50 here, zirconium, and you can see here like 250 or something, right? It's almost like more than 5 times or 6 times change. And here it's almost from nickel from 0 to changing up to like 200, right? It's like 100 times, 200 times like variation. So this is the magnitude scale of trace element variation. So you can understand if you plot in a suitable diagram these variations with major elements, right? Major elements will show you very slight variation, but trace elements instead will show you huge variations, very big variations, right? So this is very important for us to understand geochemical processes. So that's why trace elements are considered as important components in igneous systems, right? So I think now you can understand uh, the sensitivity of uh, changes in geochemical processes are mainly reflected by trace elements rather than major elements, right? Major elements also play a very big role, but in different ways, okay? But in the trace element case, it's very sensitive, and therefore they will show very large changes, and also they are present in very small quantities. That's why they show uh, large anomalies. Okay, right. So there is another important point that we have to consider, which is element distribution. Okay, element distribution means how different elements are fractionated, how they are separated into different phases. This is the very simple definition of fractionation or distribution, elemental distribution, right? In Earth systems, in different components of the Earth, Earth's materials, you have a lot of materials, solid, liquid materials. During different geochemical processes, the elements are separated into different phases, different components, right? It can be a rock, solid rock, or a melt, whatever. So the Goldsmith classified the elements, who classified the elements, has made a rule, set of rules also, right? There are 3 rules we call Goldsmith's rules on trace element distribution. Sorry, not trace element. Yeah. not, I mean, elemental distribution, you can call it elemental distribution rules of Gauss-Smith, because there is another rule for trace elements separately, but anyway, just we'll keep it like that. Gauss-Smith's rules for elemental distribution. Okay, right. So if you consider two ions, that means two elements which are available for exchanges within geological systems, right? If you have two ions with same valence and radius, that means same size and the charge. Okay, do you remember there is a important parameter we derived from the valency and the radius size, right? So you see ionic potential, right? This is the ionic potential. We use the number 2, right, as a critical factor to divide high field strength elements and low field strength elements. That means the size, if it is small and if it is charged highly, that means valency is high, ionic radius is small. Okay, so you can group them, small elements with but highly charged, and also you can classify another group, large elements or ions. Actually these are cations, right, because they are participating in reactions. Large but low charged, that means the charge is low. So that is ionic potential. So we termed, I mean, it's a boundary condition like 2 we used for classification of these particular elements, right? So this is important. So charge and size is important because that matters how these elements can be replaced, or these ions can be replaced in phases, either solid phase or liquid phase. That means minerals, right, available in igneous systems. So the first rule says the ions with same valence and radius should exchange easily and enter into the solid equal amounts, in amounts equal to their overall proportions. That means if you have similar type of ions, that means size and charge both, if they are similar, right, so their fractionation is equal. That means amounts they are entering into either solid phase or liquid phase will be equal, right? So there is no preferential fractionation in that case. Everything is going there in equal proportions, right? So if you had them in 2:1 proportion in the original source, in the result or the resulting liquid or resulting solid or the residue, we'll also have them in the same proportion. Okay, so that means before the melting or before the crystallization or whatever the process, there will be no difference in ratios. They are mutual ratios. That is the first rule. And the second one is if we have two ions with different radii but the same valency. Size is different, right? Size is different now, but the charge is same. So, but there are two different or the two separate types of ions there. So in that case, what happens? Okay, there's a disconnection. Can you hear well? Someone should answer. Can you see the screen also? Okay. Right. So the second rule says if the same, just a minute. Yeah. Same charged but different sized that ions were there, then their the incorporation into the melt or the solid will be different. Okay, so what happens? small ion is preferentially incorporated. That is the possibility there, right? The second rule says small ion is preferentially incorporated into the solid or the liquid. That means for the solid, there is preference for the small ion. Okay, so if you have two ions of two sizes but same charge, right? So to the solid, that means to the residue, what is more preferentially incorporated? The smaller one, right? The smaller one will be going preferentially to the solid. That means to the melt, it will contribute only a little. Okay, but it does not say, or it doesn't happen actually. The element goes to the both phases, but the amounts are different, right? But in the previous case, the same proportion, because they are of same size and also the same charge. Here the same charge, but the size is different. So the small one will preferentially go into the solid. Okay, so this is what happens in melting. For example, you can see here, sorry, you have liquid. You have liquid here, and olivine means you have a solid here. Okay, so in between what you have is liquid and solid, right? Liquid and solid here. So that means this is the ideal partial melting situation, right? You have a solid, you have a liquid, right? They are in equilibrium also, right? The drops of solid liquid is in equilibrium with the solid. So this is the partial melting situation. So if you have the two ions with different sizes but with the same charge, the small one will incorporate more into the solid. That means it will be more accumulated in the solid side, right? In here also it will be going to the solid, right? Not to the liquid. So this is happening under the Goldsmith's second rule. The third rule is the two ions have similar radius but different charges, different valencies. Okay, the opposite to the previous case. So in this case, what happened? The higher charge is preferentially incorporated into the solid. The higher charge will go there. In the previous case, the small ion will go there, right, to the solid, preferentially incorporated. But here, the higher charge atom will preferentially incorporate into the solid. Okay, so these are the three rules. So you have to be careful about this because when you are talking about the fractionation, all the trace elements will fractionate according to these three rules, right? So it's a matter of calculating the proportions available before melting and after melting. If before melting and after melting everything is equal, that means in your system you have all same sized and same similarly charged atoms, ions. Okay, so that is the one important aspect in igneous petrology. So you will understand why we want to learn these principles, what kind of usages are there in the future. Okay, right. So we will go into details on chemical fractionation, right? So this is what we just talked about. The Goldsmith's rules determines the chemical fractionation. So the simple definition of chemical fractionation is kind of uneven distribution of ions between two phases, right? Two phases. We call competing phases. That means they are in touch with each other. Okay, they are in equilibrium actually. The competing means they are nothing is going to react with another. Okay, that's the thing. In equilibrium situation, all these things happen, right? If equilibrium is breaking, then the competition is over. One will react with another. Okay, so we'll see one component called I, right? It can be an element, right? Exchanging between two phases, right? These two phases are essentially solid and liquid, right? We are talking about solid and liquid because we are discussing about melting and crystallization also. Still, we did not start crystallization, but we are talking about the same scenarios. That means we have two phases, one solid and liquid. Okay. In equilibrium condition, you can have similar similar amounts there, right? If they are in equilibrium conditions, right? But if they are fractionated, actually, if they are fractionated, then you will have definitely different amounts, different ratios. But for the equilibrium constant, because we are talking about a reaction, because it is just now in equilibrium condition, that means you can write that in this way. Okay, you can write it in this way, like if you have A and B, it will be like in equilibrium situation. So you can write down an equilibrium constant also for that, right? K, equilibrium constant can be written there, right? So we normally take the activity of the component, right? Activity of the ith component in the solid, because we are talking about I component, ith component, because it can be A, B, C, D, F, G, H, or whatever components. So just commonly we consider one component, say I, or you can say N, nth component, or whatever, it doesn't matter, right? So equilibrium constant is defined by the activity of the element I in the solid phase divided by activity of the solid ith element in the liquid phase. Okay, so this is the definition. By definition, the equilibrium constant is like this, right? So in other words, you can write like this also, activity. You can remember your A levels, I think, and first year chemistry. Activity can be converted, I mean, is equal to concentration. X means concentration of that element or that ion, whatever, into its activity coefficient. Okay, this one is activity coefficient. So you can have the product of these two as equal to the activity, right? If you have concentration terms, right, then you need to know the activity coefficient, how to calculate the activity coefficient. For that, you have to go for a separate formula. Okay, ionic potential and all you will have to get into know, right? So for the time being, just suppose you know the ionic, what is it? Activity coefficient and also the concentration, then you can calculate the activity of that particular ion in that phase, solid or liquid, right? So this is the definition, and we will use these things in later our discussions. Okay, remember this relationship. Okay, so I mentioned that the trace elements behave according to another law, right? The Goldsmith's laws are just about the distribution of trace elements in systems, in igneous systems. But the behavior of trace elements, that means the concentration determinations of trace elements in different materials, in different phases, is according to Henry's law. There is a law called Henry's law. So this Henry's law states that the activity of a particular element or ion has a direct relationship or is directly proportional to their concentration, right? Actually, that has it's a kind of a definition of the previous one right here, right? Activity of a particular material or phase is directly proportional to the concentration of that particular one. Okay, so it's X. So this is the relationship under the Henry's law. So for example, if you have X amount of nickel, say the concentration of nickel in a phase is X, right? Not in a phase, in a system, right? Before melting, you have a system here, right? Suppose the mantle, Earth's mantle. So before melting, it has X amounts of nickel. And if due to some reason, if you double this, if you make it double in the system, right? What happens? Because in the system you have different phases, several phases, you know, olivine, pyroxene, OPX, CPX, everything is there, right? So if you had X amounts in the system, X amount of nickel in the whole system, not in each phases, right? In whole system. And due to some reason or some igneous process, it was doubled, right? Suppose, then what happens? It will double all the nickel in other phases, right? Actually, this is not X amount, this is the concentration, right? Say C amount was there, C ppm or something, right? X is the general term for the concentration, right? So you had C amount of nickel, C ppm, right? Amount of nickel in the system. But due to some reason, maybe magma mixing, another magma came into the mantle and mixed with that and doubled the concentration of nickel. So as a result, it should double the concentration of nickel in all the phases, right? It will double. It doesn't mean, doubling doesn't mean that if you had 10 ppm in your system, right? If you had 10 ppm in your system, and after making it double by the geological process, right? Whatever the geological process is, it made double. So that means it should be now 20 ppm, right? You have olivine here. You have olivine or OPX, CPX. What else? Olivine, OPX, CPX, spinel, whatever, right? Some phases can be there. So all the components or all the other phases will also get doubled in with respect to the nickel concentration. It doesn't mean that everything will have 20, 20, 20, 20. No, right? Because olivine can take some amount of nickel, OPX can take another amount, pyroxene another amount, like that, right? Because you just learned about the fractionation, chemical fractionation, right? Everything cannot go into equal amounts because they are different phases, they are different solids, right? They are different solids. Phases means different solids in this case. It can be a liquid or whatever, but in the mantle, you have solid phases here, right? So maybe here you had some amount of say X amount, and here maybe Y amount, and here maybe Z amount, right? But since the system doubled its components, its nickel amount, all the phases should also double it. That means the resulting system after this process completed, all these all these phases should also have doubled nickel concentration. That means 2y, 2x, 2y, 2z like amounts. Okay. The altogether it should be 20 ppm in the system, like that. Okay. So so nickel within each phase will vary in proportion to the system concentration. So that is the simple interpretation of this Henry's law. Okay. So because all these activities are directly proportional, that means the concentrations will be directly proportional to the changes they are incurring. Right. This is another important matter with regard to fractionation of elements. Okay, during the chemical fractionation, these type of things happen. Right. Just keep in mind, because in some problems you will just simply get a statement like this. The system doubles the nickel component and then calculate this much in the resulting system or something like that, right? So you should just clearly understand, if it doubled in the system, each phase should double its own amount, right? That means its respective concentration, right? It doesn't mean that everything will be equal to 20 20 20 in this case, right? So the other important term that we discussed last week also, that is the incompatible elements, right? The property of incompatibility, right? So incompatible elements are concentrated in the melt. That means melt loving elements, incompatible elements means. So in these cases, the equilibrium constant, if you consider, or the distribution coefficient, whatever, right, will be less than 1. How that can happen? This is the definition of K. Remember, concentration of the solid of a particular element divided by its concentration in the liquid, right? If an incompatible element is there, right? If an incompatible element is there, that means it should be incorporated much in the liquid rather than in the solid. So you have a bigger term here and you have a smaller term here. So that means obviously it should be less than 1, because this is the ratio. Okay, so that's why it's less than 1. KD should be less than 1. But in the case of compatible elements, they are always concentrated in the solid. So therefore, it should be giving you a ratio greater than 1 always, right? Just keep that also in mind. This is also important, right? So far we normally consider about systems with equilibrium constant, or I just mentioned here as a distribution coefficient. Why we use distribution coefficient and equilibrium coefficient both? Normally this distribution coefficient is used for dilute solutions, dilute systems, right? For example, the solutions you have with minor amounts of material dissolved there, okay? There you can directly substitute the concentration ratio to calculate the distribution coefficient. That's why we call it distribution ratio rather than equilibrium constant. You are directly taking the concentrations, concentration of that particular element in the solid divided by concentration of that in the liquid, right? That will give you the distribution coefficient, and this is not the equilibrium constant. This is not KD, right? This is not equilibrium constant, because for equilibrium constant, what do you need? You need activities, right? Not just the concentration. You need activities, right? So activities ratio will give you the equilibrium constant. So to get the activity, you need to have concentration and also the coefficient here, right? Activity coefficient here, right? But in very dilute system, you can forget about this activity coefficient, and you just mention about a distribution coefficient, because you are taking only the ratios of the concentrations, right? So that is the difference. Okay, do you understand? Do you have any question or any doubt until here? Any question? Okay, right. So I think you can remember we divided incompatible elements into 2 subgroups, right? high field strength elements and low field strength elements, right? These two subgroups, high field strength elements and low field strength elements. Based on what? What did we use there? Ionic potential. Okay, we use the ionic potential to divide them, whether they are greater than 2 or less than 2, right? That means charge size ratio. Charge size ratio. So the high field strength elements, usually you can put everything which is included here, right? Rare earth elements, thorium, uranium, cerium, but typically, very typically, we take the high field strength element ratios as zirconium, hafnium, niobium, tantalum for our easiness of interpretations, right? But in fact, if you see the ionic potentials of these other elements, including rare earth elements, those they will also be falling under the high field strength element group, right? So if you take the periodic table, although we typically cage only these 4 elements as the high field strength elements, in fact, these rare earth elements will also come into that, right? That is possible. But rare earth elements have different properties, other properties. Therefore, we separate them out from these high field strength elements, right? They do not equal in geochemical properties apart from their ionic potential. That's why we take them out from to a different group, but still they can be included as high field strength elements, right? The low field strength elements are also called another term, that is large ion lithophile elements, right? The elements like here, potassium, rubidium, cesium, barium, lead, strontium, europium, right? These are called, another term is there, alkaline elements, right? Remember, alkaline elements, rubidium, strontium, potassium, calcium like elements, right? These are alkaline elements, as well as you can call them large ion lithophile elements. Large ion lithophile elements, right? If you compare their properties, their geochemical properties, you can understand these the low field strength elements or large ion lithophile elements are very mobile. They can move from one system to another easily. But high field strength elements are not easily mobile. They are immobile. We call them immobile. That means they will not easily move from one system to another. Fractionation happens, whether they are fractionating into solid or liquid, that happens. But this is mobility is another thing, right? Mobility means whether these elements can easily be changed due to a process, another igneous process. Okay, so the mobility, for example, if alteration happens, right? If alteration happens during the ascent of magma, or during while the time they are residing in the interior, these large ion lithophile elements can easily be altered. That means they can be easily mobilized into a circulating fluid or circulating hydrothermal liquid or whatever like that, right? But these HFSCs or high field strength elements are not easily taken out from that system. That is the difference, right? It's not a fractionation, because fractionation happens only during melting and crystallization. But alteration or hydrothermal circulations, interactions, like such processes are other processes, other igneous processes taking place within the Earth's interior, apart from melting and crystallization, right? So those processes are determined based on the mobility of elements, right? Whether they are mobile or immobile. That's the difference. Okay, so if we see the charge, ionic charge, and the ionic radius of these elements in a graph, it's possible to make a line like here, right? This is the ionic potential 2, because this is the boundary. If you divide the charge and the size, okay, that is the ratio, right? We are taking, just remind here, charge size ratio. The boundary is 2, right? We took the boundary as 2 for division. So you can see the same in this diagram also, in this chart. So if you divide this number with the relevant number here, okay, so corresponding number, if you use both these numbers, you will get a value like 2, okay. So this is a line dividing low field strength elements and high field strength elements. So here you can categorize. This is one of a unique plot with respect to the charge and size ratios. Okay, so another aspect that we need to consider is the factors that determine the compatibility, right? So always we mentioned that there are fractionations, right? There are chemical fractionations of elements, right? So what are the factors, or what determines these elements to fractionate into different phases in variable amounts? So there are several things that we have to consider. So actually they are determined based on what type of materials they are involved in, right? Melt, composition, and mineral. What is the mineral, right? Because based on those, only these elements preference is determined, right? So let's see. You can see here one term called partition coefficient, right? A new term called partition coefficient. We didn't learn that yet, right? So partition coefficient means the concentration of a particular element in a solid phase divided by concentration of that element in the liquid phase, right? So that's why we put it CS divided by CL. It's almost like the equilibrium constant, right? Remember, we took, I mean, the distribution constant D, right? Something like that, right? It can be termed the partition coefficient because if you are just referring individual element there, right? If you are referring a phase or a molecule, then you have to consider different components. So that's why in reactions we take different phases, and then we determine the equilibrium constant. But here we take only one element, which is fractionating into a single phase, right? So we have different phases: olivine, OPX, CPX, like many phases are there, right? And if these phases are available in different melts, in different systems, right? For example, it can be a basaltic system, or it can be an andesitic system, or it can be even a granitic system. So that means system is different. System means the overall composition of that particular igneous environment, right? Whether it's a granitic melt, or whether it is forming a basaltic melt, or whether it is forming andesitic melt, whatever, as a result of the original source, right? For example, the mantle melting can result basalt, as you know, right? Mid-ocean ridge basalts. At the same time, it can result a evolved composition like granitic composition, like the acidic composition, right? That is also possible. So in that case, in a granite also you can have this plagioclase or pyroxene or whatever the elements, and also in a basalt you can have the same element, same phases, same minerals. But depending on your system, whether it is basaltic or whether it is granitic, that means whether it is mafic or felsic, like that, right? The amounts of elements which can partition into or which can fractionate into is different, right? But uh, that partitioning is mainly controlled by this partition coefficient parameter, right? For that, we have to do some experiments and then we calculate these partition coefficients. Okay, so these are experimentally determined partition coefficients, which is published in Rollinson 1993. So this is also a very important book, right? This is a book, not a paper. So this is also available in the science library, right? So some of the relevant chapters you have to read. Okay. Uh, the title of the book is Using Geochemical Data. Okay, Using Geochemical Data by Rollinson, the year 1993. So this table is also available there. So there are partition coefficients for the commonly used phases and commonly used trace elements, right? Here we have trace elements and including rare earth elements, right? So these are alkaline elements and we have rare earth elements also. And you can see different numbers. These different numbers are calculated based on experimental results, right? So in this case, they have considered basaltic and andesitic systems. But if you consider a granitic system, these numbers will change. It will be different, right? Because in different systems, the amounts of these elements which can partition is different, right? Based on the composition. That's why, because the composition in the solid and composition in the liquid matters for calculation of the partition coefficient, right? So if in a granitic system, these numbers will be changing, right? Giving a different set of numbers as the partition coefficients for granitic systems. So always remember, you have to select the correct system also for your interpretations if you are to do some calculation with regard to this. First of all, you have to see whether you are given the relevant set of partition coefficients. Okay, you don't need to keeping this in mind, but you will be given these all numbers, right? Nobody knows these numbers unless you refer a textbook. Okay, but this is very important parameter. Okay, so this is about each phase, right? Each mineral, each phase, right? It can be multi-phase, right? Maybe one phase, two phase, three phase, five phase, many, right? So for each phase in a given system, right? System is given, and you're in that system you have some phases, right? Maybe only olivine there. Maybe you have some CPX also. So likewise, in that system, with respect to the phase that we are considering, the elemental partition coefficient will be different. Okay. So if you take a rock as a whole, because a rock is made up of different phases, right? The rock is made up of different phases. Therefore, we should be able to find out the partition coefficient of a particular element in a given system for that rock itself, right? Not just the single phase, but for the whole rock, the entire rock, right? That is also there. It's called bulk partition coefficient. or bulk distribution coefficient in such a situation. Okay. So for bulk distribution coefficient determination, or even yeah, you have to consider the weight percentage of minerals. That means the modal percentage matters, right? So you know, you get a thin section. If you get a thin section of that particular rock, then you identify different minerals there, and you can calculate a percentage of each mineral. That's actually a volume percentage, right? So more precisely, it's a volume percentage. Although we consider it as just a model percentage, that's fine. It's also okay, right? But in precise terms, it should be a volume percentage, and your percentage calculated should be converted into the real volume percentage that is occupied by each mineral in the rock, right? So there can be different minerals in your rock. They may have occupied different volumes, but we visually determine that percentage as a model percentage, but that's fine. That weight percentage or that model percentage can be taken here into weigh that amount of mineral mineral. Okay. So if we want to calculate the partition coefficient of a particular element, because partition coefficients are available only for elements with respect to their partitioning into a different phases, right? You have different phases, as we saw in the previous slide. Different phases here, like different minerals. But now we are going to calculate for the whole rock, right? Not just for each and every mineral. So for that, we need the modal percentage or the weight percentage of that particular mineral. And then the partition coefficient of that element in that particular mineral. That means you need to know these numbers as well, right? Because this is the partition coefficient of that particular element in that mineral. In CPX, this is the partition coefficient of lead in this case, right? In a basaltic and andesitic system. Okay. If it is a granitic system, then this number will be different. It may be some other number, right? But still, you know, it's CPX and rubidium you are talking about, right? So if you take lanthanum, for example, the partition coefficient of lanthanum in olivine, right? In a system of basaltic or andesitic system is this number, right? This is the number, relevant number. This is the value, right? So likewise, all these numbers have their own status based on the system as well as the phase, right? But when it comes to a rock, you have to consider all the elements, all the minerals they available there, and take their partition coefficients with the weight percentage of each of those minerals. That means if you want to calculate the bulk partition coefficient of neodymium, right? Here you have neodymium in a rock which is composed of all these minerals. Suppose you have a rock which is composed of all these minerals, and now you are going to calculate the bulk partition coefficient. So in that case, you need to know the partition coefficient of neodymium in olivine, partition coefficient of neodymium in OPX, CPX, like that. Everything you need to know. Plus, you have to know what the modal percentage of this each mineral, right? Then you can make it a proportional summation and then find out the partition coefficient. So this is the formula for that. So you have the modal percentage of that mineral or weight percentage or whatever, volume percentage, but anything is okay. Okay. it should be a proportion, right? And then it should be multiplied by the each individual partition coefficient of that element I in this case, right? That will give you the bulk partition coefficient of element I in that rock, right? In this rock. Okay, is it clear? We can do an example for that, right? To calculate, to see how we can calculate that. But you need to understand the concept first. Do you have still any question? Or are you still okay? Okay, we'll see one example then, right? This is the example. We have an example. Let's say hypothetical garnet lozolite. What is lozolite? Remember, lozolite is a mantle composition, right? Mantle rock, lozolite. It can have olivine or PX, pyrox, CPX, like those minerals. Since it has garnet, normally we don't take garnet in mineral classification, I mean the mantle rock classification. If garnet is present, then you just make it a prefix like, and then garnet lozolite. Okay, so this is a mantle rock, and the hypothetical composition 60% olivine. These are the model percentages. Okay, 25% orthopyroxene, 10% CPX, and 5% garnet. Right? They are given all by weight. It doesn't matter whatever the weight. Right? You can have your own visual estimation also as the model percentage. So using the data given in this table, the previous table that we referred just now, to calculate the bulk partition coefficient of this iridium mineral element, sorry, ER, right? So you have this iridium, the partition coefficient given. Remember, we are using this formula, right? We are using this formula, and what is the partition coefficient? I mean bulk partition coefficient. What we have to do? We have to take the summation, right? We have to take the summation of all these product, W into D, right? Plus W into W1 into D1 plus W2 into D2 plus W3 into D3, like that. Whatever the number you have, the minerals, right? So this is it. So 60% of olivine you have. So what is the olivine partition coefficient of that? Olivine here, 0.026. So you have 0.026 here into its model percentage, 60.6, right? 60%, 0.6. Plus, you can take 23. What is 23? Oh, sorry, 25. That is orthopyroxene, right? OPX. Partition coefficient is 0.23, right? So you can have 0.23 into 0.25. So likewise, you can do the addition here and calculate a value for that. This is the bulk partition coefficient of a garnet lozolite, which produces in a basaltic system. Means here we considered basaltic and andesitic rocks, like, right? The idea is this original garnet lozolite produces a melt of basaltic to andesitic composition, right? Because this melt is in equilibrium with the solid here, garnet lozolite, right? That means it is in equilibrium with these minerals which are available in the rock. That's that's the idea behind that. If it is producing a granitic melt, then you have to definitely refer to another table which has the relevant partition coefficients. Okay, so write down this example. You don't need to take down this table, but you just take down these values as the partition coefficients. Okay, you can just have a look into this table and find out some values are really high. See, 14, 5, 7, 29, like very, very big, while some are having very small values, 0.01, 0.007, like that, right? Some are very small. Why is that? You take olivine, okay, you take olivine and you take nickel. See, the number is very large, it's 14. So what does it mean? So what is this number refers? 14 means what? How it is derived? From this one, right? Concentration in the solid divided by concentration in the liquid. So what does it mean? For the element nickel in olivine, if you take the concentration, the solid means olivine, right? That is a mineral, because you have the mineral here. This is the residue, and your melt is going there, right? So in the liquid, at the corresponding time of this particular olivine is derived there during this melting process. You will have large amount of nickel incorporated into this olivine, rather than it's going into the melt. In melt, you have a little amount. In olivine, which is crystallizing here, will have a large amount. Okay, so therefore you will get a big number there. That's the idea behind that. So that means nickel prefers olivine a lot. Okay, during melting and also crystallization, nickel prefers olivine a lot. That means nickel is preferentially partitioned into olivine. Okay, nickel is preferentially partitioned into olivine, and if you see barium, it's not going there that much, right? That means olivine, the barium is not preferentially partitioned into olivine. So in other words, how can you say, how can you interpret this phenomena? Nickel is compatible in olivine, right? Nickel is compatible in olivine. What do you mean by that? Compatibility and incompatibility. Remember, compatibility means the preference to a solid phase. So that means nickel prefers solid phase. In this case, the solid phase is olivine. Okay, nickel prefers a lot olivine. That's the idea behind this. So in igneous systems, in mantle mainly, nickel is always compatible element, behaves as a compatible element, because it always wants to go into the solid, not into the liquid. That's the idea, right? So strontium, rubidium, barium, chromium is average, right? Is 0.7. And rare earth elements, they are very little, very small. That means almost all these rare earth elements, not almost everything, all these rare earth elements prefers liquid, right? That's why it's low here, because olivine is a solid phase, it is low. That means in olivine you don't see much rare earth elements. That's the simple indication there. Okay, so that means all the rare earth elements are incompatible in olivine. If you consider olivine, it's incompatible. But if you compare it with clinopyroxene, you just compare your rare earth elements partition coefficients with clinopyroxene. What happens? This 0.5, it's significantly higher, 10 times, more than 10 times higher than in olivine. So that means some of the rare earth elements, say from here to down, right, are more or less like to partition into CPX phase, solid phase of CPX. So that means in CPX, these rare earth elements, these particular rare earth elements are compatible. Whereas these other rare earth elements, the other half, they don't like much. That's why you have lower values, right? They don't like much CPX. They like, but not much, right? So relatively incompatible. Okay, relatively incompatible because they are not get retained in CPX. They they are thrown into the liquid mostly. That means they are incompatible. So if that particular element, if you want to uh, compare its compatibility or incompatibility with respect to the solid that we are talking about, or the solid phase, for CPX, these rare earth elements, the early half is incompatible. They are not compatible. They are incompatible. Okay, but if you consider these ones, this set, they are compatible, right? They are compatible because they seems to be much incorporated into. So what are these rare earth elements of this half? Normally, you can divide it from here to there. Light rare earth elements and heavy rare earth elements. Okay, so this set, this particular set is called heavy earth elements, and this particular set is light rare earth elements. Actually, in between you have the middle rare earth elements, right? But just forget it for the time being. So heavy rare earth elements are compatible in CPX, and light rare earth elements are incompatible in CPX. So incompatible in CPX means they do not like to be incorporated into CPX, right? So this is how you can interpret your geochemical data, right? Obtained in analysis. Okay, so you have to always use these terms in order to explain their behavior, their geochemical behavior, whether they are incompatible, whether they are compatible or incompatible, like that. Okay. And one significant change you can see here in plagioclase with respect to europium, right? EU, you have europium here, the element europium, right? You have some value 0.1 and also 1.5. Actually, this is large range is there for europium because europium is available in multivalent forms, right? 2 plus and 3 plus. So europium 3 plus is preferentially partitioned into plagioclase compared to europium 2 plus. So for europium 2 plus, you have a partition coefficient like 0.1, but for europium 3 plus, there is a partition coefficient of 1.5. That means a large number, bigger number. Compared to 0.1, it's like 10 times, more than 10 times bigger. Okay. So it's because europium 3 plus is incorporated into plagioclase structure as it behaves like a trace element, right? Europium 3 plus, I mean, the common trace elements are trivalent. Always remember, I forgot to mention that. All these rare earth elements are trivalent, okay? They behave trivalent, but if you have a divalent cation, they do not prefer going too much into these phases. That's why europium 2 plus does not get incorporated much in plagioclase in this case, right? For other phases, you don't see much big numbers for europium. That means europium cannot go much into other phases as compared to plagioclase and amphibole, right? Amphibole also can take much bigger content, okay? But amphibole, you can, for the time being, you can forget because amphibole means a hydrous mineral, okay? So that means in addition to the solid component in amphibole, actually there is a liquid component inside, right? The structurally bonded OH group is there, okay? So therefore, its behavior for trace elements and partition coefficients are little bit vague, I mean, the interpretations, and also complicated because you have a kind of a mixed behavior inside, right? You have water also there inside. So therefore, some strange things can happen in amphibole, but all the other minerals that we consider are anhydrous, uh, including magnetite, oxides, right? Not only these, there are so many other minerals you can consider, but frequently for mantle melting, we have to involve these phases, right? So amphibole comes rarely in our interpretations unless you are going for a very complex system. Okay, right. So we talked about the partitioning, and we know that the traceable elements are strongly partitioned into a single phase or a mineral, right? So we already talked about nickel behavior in olivine, right? In this the previous table, it's like 1 point, sorry, it's like 14 uh, in previous case, right? So you can see the concentration variation. I have shown you this table before, this figure before. All for the all silica compositions for the entire silica range from 40 to 80. This is ultramafic, extremely ultramafic, and this is extremely acidic. 80% silica means very high acidic rock. Should be very whitish rock, whereas this should be very dark rock. Okay, because the amounts of the presence of amount of silica in different quantities determines the color of the rock also, right? So you can see some variation of nickel, and you can see here a kind of a deviation, right? It's a special point there, right? It means uh, the 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 system evolved in such a manner that some small amount of nickel was fractionated from from the original system. So you have original system and you are melting it, forming some melt. Okay, so you are forming melt means you are changing your silica composition also. Initially you have some given number, may say X composition, and this X composition will be changing to X1, right? X1, and then gradually X2, like that. You can change, right? Either this way or this way, right? Increasing silica or decreasing silica, but in this particular example, we take it as decreasing silica, right? This way. So at a certain point, you can see a drastic change of nickel, right? Sorry, the nickel was changing slightly like this, right? Because it's here 0, and then maybe 50 here, right? For a large silica range, right? From here to here, 72, say 55 silica range, there was only little, I mean, relatively little amount of nickel changed, right? Up to 50 or something. But all of a sudden, what happens? In a very narrow silica range, changing range, right? Very narrow change here. The final nickel composition is like more than 200. Okay, from 50 to 200 it has changed. Drastic change has happened. So what does this might indicate? From here to here, there is no much nickel fractionated. That means, right? So it has been remaining with the solid a lot, right? In this original composition, you have some nickel, and lot of nickel should have been there remaining, and at a certain period, at a certain time, lot of nickel will be going out, right? It increases. So that means what is happening? The amount of olivine crystallization in this particular situation should have been increased, because if you gets lot of olivine there, then nickel will be incorporated a lot into that, right? Actually, this graph indicates uh, the crystallization behavior of olivine with respect to nickel and silica system. Okay, so you can take the same thing in opposite ways also. That means if you are melting an olivine bearing rock, then uh, you can think of how olivine can go into the melt also, right? We will take this type of examples later on, because it is too early to explain this type of different scenarios. But just keep in mind that sensitivity of nickel in geochemical systems is mainly reflected as a olivine fractionation, as a result of olivine crystallization behavior, right? Not fractionation, crystallization. Because the nickel is fractionated into olivine in large amounts, because it has a large partition coefficient, right? For nickel, large partition coefficient. Nickel has a large partition coefficient to olivine, right? Not other things have smaller ones. That's why you see some kind of behavior up to 50 ppm here, right? But all of a sudden it starts to increase. That means a lot of olivine should be there for nickel to be incorporated into. This type of changes in geochemical plots are very important, because they are very sensitive, right? That's why we always take trace elements to reflect these changes. But see, silica is just changing from 70 to 60 to 50 to 30, 40, like it's changing, but you don't see much difference there, right? Unless you have a, a spike like this with respect to another element, right? Just by silica, you are just drawing an arrow like this, right? But because of olivine, you could draw an arrow deviation like this. Okay, so that is the sensitivity of a trace element. So in igneous systems, we use these trace elements to interpret a lot of processes. All these processes we are talking about have happened in the past, right? Because we are analyzing a rock, right? We are analyzing a solid rock, which was subjected to various processes within the crust or mantle, right? Long time ago. But just using our data, we are going to the past, right? We are trying to interpret their history. That is the importance of these trace elements in igneous systems, right? So in advanced igneous petrology, always you will be able to interpret your rock systems with respect to melting or crystallization, right? Melting, crystallization, and there are some other processes also, but mainly with respect to melting or crystallization. This melting can be either mantle melting or even crustal melting, whatever, right? We haven't gone to the crustal melting yet, which is very, very complicated. But I don't know whether we will have time, enough time to go into that. But we will finish the mantle melting first. Okay, melting and crystallization then. Right. So do you have any question? Okay. Okay, we can take another example, similar type of example, but with respect to zirconium, right? But you don't, you will definitely see the difference between nickel and zirconium, because nickel showed a drastic change here, right? But if you see a similar plot with nickel, with zirconium, you don't see such a change. But instead, what you see is a very, very positive correlation. This is called a positive correlation with respect to silica. So if you take this positive correlation in this way, in this trend, what is happening here? You will see the increasing silica content. Okay, increasing silica content, and with increasing silica content, what is displayed here is increasing zirconium content also, right? It is always increasing with respect to silica. If you take silica content here and zirconium, right? Say 45 and zirconium maybe 75, and then you take another point, their silica content is 55, zirconium content is 120 or so, right? Another one 65 or something, and zirconium maybe 150. So anyway, you are increasing silica as well as you are increasing zirconium. Okay, the y-axis is zirconium. So that means you are seeing a trend like this. So this type of trend we call a positive correlation, right? A positive correlation. If your trend is opposite, that means if you have a trend in this way, right? When you increase something, and you might observe a decrease of another thing, the second particle, second variable. In that case, we call an inverse correlation or negative correlation. Right? These positive, negative correlations are also important in these discussions. So zirconium. So we'll go back to the table and see the partition coefficients of zirconium. Is it given? Oh no, unfortunately, it's not there, right? High field strength element, zirconium is not given there, but the implication is there in the figure. So therefore, you can understand they're increasing. That means, what do you mean by this increase in silica? Originally, you have a mantle material, which is very mafic, ultra mafic, right? So then you produce a residue with what? No, sorry. You take because silica is increasing, right? Silica increasing means your melt you are producing. Okay. First, you take like this. You have a mantle here, and you produce some melt, right, with some basaltic composition. Say basalt means it's a dark rock, right? It's a mafic type of rock. Maybe initially your mantle is 40, suppose 45, let's say 45 here, right? 45, your basalt may be 50 of silica, 50, the composition, right? Then your residue, if it's subjected to further melting, your residue will get more and more mafic composition, whereas your melt will get more and more felsic composition. Why? You have a basalt produced here. That means you have contributed all, some of the melting materials, CPX, OPX, like phases have already gone into this basalt as melted, but little amount is remaining there, right? But compared to the previous original mantle, the amount of CPX and amount of OPX is little. But we learned at the very beginning, olivine is contributing to the melting very little amount, right? It is not much melted into the accompanying melt there. So that means olivine is remaining there in large quantities because it has not contributed into the melt. So you have taken out all, not all, most of the CPX, OPX already. So automatically you are increasing the olivine composition in your residue, right? It happens automatically, right? So if you have 50 girls and 50 boys in a classroom, and you ask 25 boys to go away, then what is the concentration of girls? Automatically they will be increased, right? So like that, the residue gets more and more mafic, whereas the melt gets more and more felsic. That's why you can see the increasing silica value here, right? The melt gets more and more, the silica gets more and more enriched in the melt. So finally, you will end up with a very, very mafic residue plus a very, very felsic melt. That's how the granites are produced in mantle from the mantle rocks. Okay, because normally mantle produces basalts. Basalt is mafic, right? If the normal average amounts of melting is there. So if this melting continues, you can even produce a granite from a basalt, from a mantle rock, peridotite. Okay, so this is an example for such a thing. So this is the composition of the melt varying composition of the melt, and the zirconium, which is which is contributed into many phases. Not only, I mean, like in the case of nickel, it contributes only to, I mean, mainly only to olivine, right? Other phases, its contribution is almost negligible. But for zirconium, it's not negligible. Zirconium goes into almost all the phases, right? That's why it has a gradual change. It has a gradual change like this, right? If in any case, if you happen to have a very compatible mineral for zirconium, right? That means for the zirconium to be compatible into that particular mineral, preferentially going into that mineral solid phase, then definitely you will see drastic increase of zirconium like this in your graph. But in this graph, you don't see such. That means ordinary melting is taking place, gradual melting is taking place. So for almost all the phases that is crystallizing or that is melting, will take some of the zirconium into their phases. So therefore, the variation is gradual like this, not very drastic like we saw for nickel, right? Okay, do you understand? If you are taking in a direction of increase in silica, then you are talking about the melt mainly, right? If you are taking a direction opposite way, that means you are talking mainly about your residue, because in the residue you are decreasing silica content, means increasing your maficness, right? That means your magnesium oxide, calcium is getting increased in the residue here, right? So you are removing a lot of melt, means you are enriching a lot of olivine there. You are enriching a lot of olivine, means you are enriching a lot of iron and magnesium. Okay, that's what happened to the residue. But in this case, we are talking about the silica, an increase in silica trend. That means we are talking about the gradual evolution of a melt originated at a mantle melting, starting from basalt to granite. Okay, from basalt to granite. That's the point here. Okay. So just to summarize what we have discussed today, we started with the trace element behavior with respect to the compatibility and incompatibility, right? Always have this diagram in your mind, right? This diagram, what original mantle, right? It produces two components as a result of partial melting, melt and residue. So always you have to think of which phase that you are talking about, whether it is residue or melt, right? If the residue you are talking about, then the more you melt the mantle, the more you make it's highly mafic. But if you are talking about the melt, the more you do the melting, the more you make it felsic, right? So because the melt is always felsic. I mean, not always felsic, but the increasing melting means you are gradually changing the original mafic melt into a felsic melt. Because at the very beginning of melting, you have a basaltic melt, and again you have a basaltic melt, but the composition may be less magnesium compared to the previous melt, and again you have intermediate composition, and then finally you will end up with a granitic melt, right? So similarly, you are increasing the mafic composition of your original mantle, and then you will make it more mafic, and you will make it more and more mafic uh, at, at the final stage. So at the final stage, you have a very mafic residue. At the same time, you will have a very acidic melt. Okay, so these two are always we call complementary. Okay, these two are complementary. That means correspond to one to another, right? If it is highly mafic, the other one is highly felsic, like that. Okay, so it's like complementary, right? So original mantle that we discussed, which was melted from here, we call fertile mantle, because fertile means it has the ability to produce melt. Always remember, fertile mantle means the mantle which has an ability to produce melt out of it, right? Some peridotite can produce basalts as a result of partial melting, whereas some peridotite cannot produce melt out of it. So those peridotite which can contribute melt or which can produce melt are called fertile peridotite or fertile mantle, whereas the other ones which cannot produce melt are called refractory mantle or refractory peridotites. Refractory, remember that term also. That is also important. Refractory, right? If a mantle is highly refractory, means you have a lot of olivines there, right? Olivines cannot be easily melted. If you have a lot of pyroxenes, a lot of plagioclase like minerals, then it's a highly fertile mantle. That means at a lower heat amount, at a lower heat content, you can easily produce a melt. But if you try to melt a refractory mantle, you need a lot of heat, but still you cannot make much melt out of that. Okay, so during these processes, the melt here will take a lot of incompatible elements, and the residue will take a lot of compatible elements. All right. So compatible elements are preferentially gone into the melt, whereas the compatible elements are preferentially gone into the residue. So in this case, the residue will have a lot of compatible elements, and this melt will have a lot of incompatible elements. This is how the trace elements behave in a mantle melting. In crystallization also, we will talk about this later. The similar behavior will be there. That means compatible elements will go into the crystallizing phase, right? Crystallizing phase means newly crystallized minerals. And here you have already crystallized materials, right? That's why we are not talking about it. But in a melt, you don't have crystals at first. You have a melt only, right? Then you start to crystallize. So when you start to crystallize, that means you are producing a solid phase. So then definitely these compatible elements go preferentially into that. And the remaining melt which is available will be enriched in incompatible elements, because the melt likes to retain as much as possible this incompatible element budget, right? This is happening in crystallization. So melting and crystallization are the main processes that take place in igneous systems. So we have to be careful on dealing with them. Okay, so I think we talked much about the compatible and incompatible elements today. So we will have further discussion in the next week, and I would like to stop here for today. But if you have any questions, you can ask me now. Do you have any questions? I suggest you should go through your notes again and again. Otherwise, it's very hard for you to grab this some of these new terms, right? Because even you did geochemistry, but you did not deal with hard rock geochemistry. So therefore, uh, some of these terms may be not very familiar to you, right? And if those who are planning for higher studies, you must learn in depth uh, about these processes later on, because if you are going for petrology or geochemistry, isotope geology, even economic geology, right? Or minerals or crystallization or formation processes, obviously these facts will be very, very useful. Okay, so let me finish for today, and please sign the attendance sheet and submit it to the office.